Okay, so we're going to talk about stress due to bending. And again, I've gone through and put together slides that basically try to summarize these sections. Oh, okay, I did put the sections in here. 7.1 to 7.4, 7.6 to 7.9. There's my little laser. All right, so this just sort of summarizes the chapter. Failure modes. Oh yeah, we'll talk a little bit about failure modes. It's kind of neat. We're talking about the flexure formula and how you use it, what the stress distribution looks like, and beams. And then we'll talk about beam design and, well, analysis of stresses and how to use that for beam design, and then some of the design procedures. And there are stress concentrations too, just like with torsion, when we had objects under torsion or tension or shear, right? Things like keyholes or grooves, those things cause stress concentrations. Same thing with bending moments. Those also cause stress concentration points. All right. Oh yeah, I made this one fancy the other night. So let's look at some of the failure modes. This is a complete fracture, right? So something you see on like a wood beam, or they actually give you some small cast parts. Have you ever bought like a cheap? I've seen this happen with corkscrews. Cheap corkscrew or some kind of part from some cheap metal part, and the casting part breaks, and you see this brittle fracture. And that's complete fracture is typically characterized by sudden and complete breakage. Yielding. You have a beam here, and this beam might be made of ductile material, right? So it will deform, it will bend, and you'll have elastic deformation first, right? As we learned about. However, at some point, if the load is high enough, right, or applied long enough, usually it's got to be both, right? You'll start getting excessive stretching, right, and you'll get yielding. You'll pass the yield point of the steel, and you may not pass the yield point in all areas, right? So you might get, yielding in certain places, like in the flanges, and it won't fracture, but it'll start yielding, and that's going to be the first step to failure of the beam. So this is another reason why, in skyscrapers and things, they have, any steel structure, you have a fire, right? And if there's enough of a load and you heat up the metal hot enough, right, and soften it, you're gonna take the metal beyond its. Remember, those yield points are for materials at a specific temperature, right? And that yield point changes with temperature. So then you'll get beams starting to sag and such in the heat. This is interesting, this sort of local crippling. If you have a beam of cross-section like this, you might get some crippling on the flange as you start loading it up. So the rest of the beam might be fine under the load, but your first point will start failing on the flange here. So that's a local crippling, they call it. Let's see, a few more. Web wrinkling. I just took these right out of your books. I just thought they were cool to go through. Because I don't think a lot of people think about, and you hope you don't see it very often in your day-to-day life, right? Failures of beams, because that would mean that things are not working properly. So this is not something that I think most people get exposed to. I think it's worth going through, right? You can actually have a wrinkling of the web in here. I didn't actually know that this could happen until I started teaching this class. Anything with a thin web can experience that. And then fastener failure. This happens with things like fabricated beams, beams that you fasten together with, say, some kind of, in this case, it might be some kind of rivets or, adhesives, any type of fastener or welding, right? You've got this beam that from the side looks like this. You've got plates on top that are riveted in place. And if it starts failing in shear, it's gonna fail the fasteners first. Interlaminar shear, right? So you might see this with, you could even see, well, I don't know if you could see this with plywood. I don't know if I've seen plywood fail. Have I seen plywood fail? I'm assuming you'd get this out of plywood as well, unless the glue is stronger than the wood. You get separation of the layers, delamination. I've definitely seen this with certain ceramics. I used to work in a place that made boron nitride, which is this really cool laminar ceramic. And the adhesion between the layers is weaker than the layer itself, right? So if you bent it too much, it would start delaminating. So you can get this with any type of laminate structure or composite structure, plastics, right? Wood, thin metal composites. All right, so what's happening? Well, we have a beam in flexure, right? And this is what it looks like. It's got, these are not two beams. This is supposed to be the initial position, and then you apply a load and it sags, right? And this is kind of an exaggeration, I would think. Well, I mean, it might not be. I've seen people do stupid things with 2x4s. And we can look at a beam and we can divide it into two regions. First of all that work you did on locating centroids, well, that's important because along the centroid of an object is this centroidal axis. So we would have located the centroid based on the cross-sectional area of this, right? So one of these faces. And then that axis runs through along the long axis of the beam. And along the centroidal axis, this is what's called the neutral axis. So if it starts bending, your stress and strain are 0 on this axis. However, above this axis, now this depends on where the force is being applied, right? If the force is being applied on the top and your bending moment's this way, right? Your top surface is going to be in compression, right? And your bottom surface is going to be in tension. So think about if you're looking at a specific element down here, this element is being pulled apart, right? And it wants to pull the beam back together. This element up here is being pushed together and it wants to push back, right? So you get tension below and compression above. Now, obviously, if I were applying a force from the bottom, right? And there's a lot of time, most of the time, beams are being used to support some load. But if I had a load coming from the bottom, this would be reversed, right? The bending moment would be upside down. The tension and compression would be flipped. So in order to do the analysis here, we look at what's called the flexure formula. And this flexure formula tells us that the maximum stress, right? And this could be tension or compression. It's at the outer surface, and it's a function of a few things. It's a function of the bending moment, right? So we have to calculate that based on something like a shear bending moment diagram. It's a function of the moment of inertia of the area, right? The cross-sectional area with respect to that centroidal axis. That's why we did that. That's why we did all this work on moments of inertia, right? And then the distance from the centroidal axis to the outermost fiber. So when they say outermost fiber, it's basically the furthest point from the centroid. Now, this is a nice symmetric beam, right? So the centroid falls right in the middle. So your distance C is the same either way. What does that mean? Well, it means that you have a maximum stress of compression up here, and that's equal to the maximum stress of tension down here. If your beam was not symmetric, your max stress could be compressive or it could be tensile. They don't have to be the same. What else? Oh, notice here, right? Earlier we were talking about moment of inertia and how that sort of determines the stiffness of a beam, right? So you could see that for a given bending moment and a given distance c, right, of this beam, the higher the moment of inertia, right, the stiffer the beam, the lower the maximum stress is, right? And obviously the higher the bending moment, right, the higher the max stress. All right, so how do we apply this formula? Oh, I thought I had bulleted this to show up one at a time. All right. Well, the first thing is you've got, remember the stuff we did in chapter 5 where we did the shearing force and bending moment diagrams, which, yes, by the way, I still have to finish grading that homework. Sorry about that. I had some quizzes behind it. Yeah, so you determine the bending moment on the beam, and maybe you're being asked to look at a particular location in a beam, or you could be asked for the maximum bending moment, right? You have to figure that out using shearing force and bending moment diagrams. The next thing you do is you locate the centroid of the cross section of the beam. And this is the stuff from chapter 6, right? And that centroid tells you where the neutral axis is. You also compute the moment of inertia, right, with respect to the centroid. And we learned how to do that in chapter 6. So the new stuff here is now looking at this formula and saying, okay, what's the distance c from the centroidal axis to the top or bottom of the beam? And look at the greater distance, right? So you may have a beam that's asymmetric. And I think I have an example. Yeah, we do have an asymmetric beam example. And then you're going to compute the stress using the formula here. So remember, C is the greatest distance from the centroidal axis to the top or bottom of the beam, whichever is greater. M is the bending moment, and I is the moment of inertia, which you've calculated or given to you. And all this stuff you know how to find now. All right. So example 1 here. Oh yeah, this is this based on problem? I think it's based on problem 7.3. Yes, problem 7.3 is a homework problem, but I thought, you know what? There's not too many of these homework problems, and I think I assigned them all or something. But they're good practice, and I thought I'd just take this one and change the numbers. That's all I did. And we have here a bending moment. Let's see, did I, my numbers right? Yeah. Bending moment of 320 pounds is applied to a beam with a rectangular cross-section of 0.5 inches by 1 inch. Compute the maximum bending stress in the beam if there's 2 scenarios, right? So this would be like laying a beam on its short end, right? So the vertical side is 1 inch, or the vertical side is 0.5 inches. So this depends on how you orient the beam. So let's look at this example problem here. It's like there's, oh, that's weird. It took a screenshot. All right, there we go. Yeah, the camera freezes for some reason occasionally. It's my red pen. All right, so what do we have? Let me draw this out for part A. I'll just draw A right here. A is the vertical side of the beam is 1 inch. So I'm going to draw the beam like this. This is a really rough rectangle. So remember, our centroidal, our axis through the centroid is here in the middle. And here we've got 0.5 inches. This whole height is 1 inch. And obviously the distance to the centroid is going to be a 1/2 inch. Right, it's right in the middle of the beam. It's a rectangle. Our moment is given as 320 pound-inch. And what else? Were we given? We were not given a moment of inertia. All right, so our max sigma is mc over I. We know moment, c is going to be 0.5 inches. Remember, c is the distance, the maximum distance between the centroid and either the top or the bottom. So that's where the 0.5 comes from. The moment we were given I, we have to calculate. And I for a rectangle is bh cubed over 12. Now, notice the orientation, right? The I for this uses a height of 1 inch about the centroid, right? And a width of 0.5 inches. So this becomes 0.5 times 1 cubed over 12. All the units on this are inches to the 4th, right? Here we wind up with an I of, see, I better recalculate this because I made some changes. Oh yeah, sorry. 0.041, I'll stop here at 6.7 inches to the 4th. This is our I value. So the max stress for this particular beam in this orientation is going to be 320 pound-inches times the distance c, which is 0.5 inches, divided by I, which is 0.04167 inches to the 4th. And we wind up with 39.7 pounds per square inch. And I'm going to round this to, I'll round it up to 3840. So that's the maximum stress in this beam if you orient it in this direction and apply bending moment of 320 pound-inch. So the inherent assumption here is that you've got some load on top, which is applying that moment. So this is part A. Let's look at part B. And I think you can figure out in part B, we're going to lay this thing on its side. So this is our centroidal axis here. Let me put the dimensions in. Here we've got ½ an inch, but this distance here, 0.25 inches. So this is your new centroidal axis. Our sigma max now is still mc over I, right? Except these are different. Well, these two things are different. The moment is the same, right? The moment is still 320 pound-inch. But C now, see here. This sounds like a Dr. Seuss book. See here now. C, the letter C here is the distance the max distance from the centroidal axis to the top or the bottom. And again, it's symmetric. So C is now 0.25 inches. So notice up here, C was 1. Now C is 0.25. So this is going to make, this should reduce the overall stretch, right? But let's look at our I value. I. So here we've got BH cubed over 12 for a rectangle. But what is B and H now? Or what are B and H? These are different, right? Up here, base was 0.5, height was 1 inch. Right now, we've got base is 1 inch. Height is 0.5 inches, and that's cubed. So the moment of inertia for the beam in this orientation is 0.01042 inches to the fourth. This is like, this is about a quarter of the moment of inertia with the beam oriented vertically, right? So the moment of inertia, remember, is representative of resistance to bending or stiffness, right? So right now you can see, oh yeah, this is less resistant to bending than in the other orientation. And common sense kind of also tells you that about this beam as well. So we're going to calculate sigma max. 320 pounds per, or pound inch. We've got, where the hell, oh, 0.25 inches. That's my C. And then my moment of inertia, 0.01042. This gives me a sigma max of, oh, looks like I just rounded this answer. .76. Well, let me write this here. Let me just do the number real quick. 320 times 0.25 divided by 0.01042. Oh yeah, 76, 77.5. So here I get 76. I just rounded to 7680 PSI. Oops, I'm zoomed in a little too much today. Yeah, so notice that's twice the stress, right? Which kind of makes sense. We cut our moment of inertia by a quarter, right? Approximately a quarter, and we cut our C by a quarter. Oh wait, where's the C? 0.5. Sorry, by a half. Right? But the moment of inertia is, yeah, so it's a half and a quarter. So that makes sense, right? It's about double the stress. Well, it is double the stress. So that's how you would do a problem like this based on the orientation of the beam, right? And typically you get a simple, you know, something simple like a rectangle is fairly easy to do. Are there any questions on this problem, this example? All right, let's see. The next one is, do I have a slide first? No, I don't. All right, let me, yeah. So this just basically demonstrates the formula and the max stress and stuff. Now, there's some conditions on using this formula. So when you use this for more complicated situations, the beam in general needs to be straight or nearly straight, right? it can't be twisting as well. The cross section has to be uniform. So some kind of uniform material, or the cross section can't vary along the length, right? Like the flange can't get smaller as you go down the length of the beam. So the cross section has to be uniform, and this uniformity applies both geometrically and material wise also. All loads and support reactions must act perpendicular to the beam axis. So if your beam is running lengthwise this way, right, the support reactions have to be acting perpendicular to it, up and down, not at an angle. And the beam must be in pure bending, so no twisting of the beam is allowed to use this formula. Length versus depth. Oh yeah, this is an interesting one. So length versus depth, and they're talking about length, the overall length of the beam spanning, right, some distance. So if you lay a 2x4 down, the overall length from one end to the other has to be the ratio between the length and the depth, right? So how deep the beam is, or thick the beam is, has to be greater than or equal to 10. So that's the typical applicability. It's got to be much longer than it is in height. The material must be homogeneous. Yeah, I sort of touched on this up here. The cross section must be uniform. This is geometric uniformity. This is material uniformity. So the beam needs to be homogeneous. And the material should have the Young's modulus in tension equals the Young's modulus in compression. So the beam needs to be like all one material, and that material should be such that the Young's modulus in tension and compression are equal to each other. Loading stress does not exceed the proportional limit, right? So remember as we had a graph, we had stress versus strain, and that first section, that straight line section, the elastic region, right? When you started to deviate from the straight line region, that's where you started exceeding the proportional limit. So we want to stay in the elastic region in order to use this formula, because at that point, if you're not in the elastic region anymore, you start to get one of those failure modes, like you might start getting yielding on a beam, right? And that the stresses are going to be all over the place, right? Some places are going to carry more stress than others. It's not going to be a uniform stress. And you can't have any failure from instability, right? Buckling, crippling, etc. And finally, the section of interest must not be too close to the concentrated loads. And this is more of a, ideal, again, this is ideally applying that, that formula. If you're too close to a concentrated load, right? Just like if you're too close to one end of a piece being pulled apart, right? That stress needs some distance to uniformly distribute over the load or over the cross section. So if you're too close to the concentrated load and it hasn't fully distributed, and concentrated load points, right, are going to have some of the locations of higher stress concentration, and you would try to catch those. There's other ways you'd catch those besides using this flexure formula. And in fact, now we have computer modeling that can do, they can tell you the stress in all different parts of the beam very easily, just sort of looking at it visually. All right, remember, this is condition number 4. So the beam must be in pure bending, no twisting. This is just a graphic they had in the book, which I thought was useful to look at, right? So these are loads that are acting through the axis of symmetry. These would be in bending, right? Assuming, again, the support is also, it's fully supported, or it's supported at a point, right? Notice the point of application of the load is through that central axis, right? That axis of symmetry. Now, if you do something like this, right, where a load is not acting through the axis of symmetry, you're going to get some kind of twisting. So imagine the load is being applied on this beam here. The beam is going to be bending, but it's also going to be twisting a little bit because this is not a symmetric, none of these are symmetric. So the load is being applied in the middle. It's not being applied at the centroid. So you're going to wind up with twisting of these beams. So you got to be careful of that. Here's a symmetric section. Oh yeah, the thing I want to say about this. So this is a symmetric section, right? We saw this briefly in the other slide. Notice the distance from the centroid to the top or bottom is the same, right? So that means the maximum compressive stress is equal and opposite the maximum tensile stress. And notice this, right? It goes through 0 at the neutral axis. And the bending moment here is shown this way, right? So this is compression, this is tension. Now, if you have a non-symmetric section, you have something like this, right? Look at the top. The top has this flange here. The bottom is this straight section. Notice the centroid now is moved up. So your neutral axis is up here. Well, what does that do? Well, it means the largest distance from the centroid to the outer fiber is the bottom, right? So sigma max for the overall beam is actually the tensile sigma max. There's two different ones. Sigma max compressive is up here, but it's not the same magnitude as the tensile stress, right? It's actually less. So you're going to be able to calculate two different max sigmas, one for compression, one for tension. What are we showing down here? We're showing the equations. Here's sigma max. Stress inside of a beam, right, with distance is going to be sigma max. So first you calculate the maximum stress. Then you take the maximum stress and you multiply it by the distance you are away from the centroid. So if you were halfway here, right, if C was 2 inches, right, halfway would be half the stress. It'd be 1/2 times the max stress. So it's just a ratio. Notice this is it's a linear relationship here and here, right? So it's just a ratio between the distance that you're looking at of interest and the overall distance. And we'll do an example on this. Yeah, in this particular beam's case, the maximum sigma is actually the tensile stress, right? So we're using the distance C sub T down to the surface and tension. And what is this? This is, oh yeah, so sigma max is here, shown here, CB, right? I just rewrote it with the notation of that diagram. All right, so let's do an example. We should be able to get through this. This is another example now, and this is a beam that's obviously not symmetric. And I think I took this from example 2 in your book. I don't know if I changed the data at all. Probably not. All right, so I've got this beam, and it carries a load, and that load generates a bending moment of 100,000 pound-inch in the beam, right? And you're given a bunch of information here. You're given the moment of inertia, right? So you don't have to calculate that. And you're given the centroid, 3.25 inches up from the bottom. So that tells you the centroid. And that corresponds with point D. And it wants you to figure out the stresses due to bending in the beam at 6 axes, A, B, C, D, E, and F. And then plot a graph of stress versus position in the cross section. When you compute these stresses, we're going to be saying if they're in tension or compression. So let's look at this on a piece of paper here. All right, what I'm going to do is I'm just going to draw a side view here, a very rough side view. And I'm going to overemphasize this. So this is what the beam would look like from the side, obviously exaggerated, right? And we've got this bending moment. (100,000 pound-inch). So this is, let me just label this side view. Now your centroid is actually kind of a, draw it in red here. Runs through the beam like this. This is your neutral axis. So down here, we're in tension. And up here, we're in compression. So your sigma max is MC over I. And let's put some numbers in here. We've got I, we've got M. This is pound-inch. I is 18.16 inches to the fourth. All right, what is C? Anyone want to take a guess at what C is here? You probably can't even read the numbers. Oops.
I'd guess like probably 3.25 because it looks like it's a little bit higher. Oh,
It looks like what?
never mind. It's on the other side.
Other side.
You were
Okay.
asking.
I was asking what C might be. The letter, the value C. Remember, C is the distance from the centroid to the. It's the maximum distance from the centroid to either the top or bottom of the beam. So let's look at this. The centroid's up here. We're given 3.25 inches from here. The overall beam's 5 inches, so this is like what, 1.75 inches. So the overall distance that we're using for C is 3.25. This is going to give us the max stress. Now this max stress is going to be a tensile stress. Because we're looking at the distance to the bottom of the beam, right, which is in tension. So sigma max here becomes 17,896 psi, which I'm going to round up to, well, let me do a few things here. Sigma max is equal to sigma A, right? We're supposed to find the stress at A, B, C, D, E, and F. And that's going to equal 17,900 psi. And I'm going to put a T next to it for tension. Just like we used to do when we were doing method of joints, right? Looking at the members, are they under tension or compression? Or under tension. All right. So why don't I go now and compute all the rest of these? So let's look at sigma y equals all right. Now, the stress at a given distance from the centroid, y, right, is just the max stress times the ratio of the distance divided by, the distance you're interested in divided by the distance from the centroid to the maximum location, right? So let's look at what this formula gives us. And let's just look at point B first. So let's look at point B. Sigma B is, we've got sigma max. And this is PSI, right? What do we got? Well, for C, We know what C is, right? We used it up above. It's 3.25 inches. Now, what's Y? Well, B is this distance away from the centroid, right? It's 3.25 inches minus 1. So it's 2.25 inches away from the centroidal axis, right? So this is 12,392. I'll round this to 12,390 psi, and this is also in tension. And why is that? Because that is below the centroid axis, right? It's below the centroid. It's still on the tension side. So that's why it's in tension. Sigma C. So C, this is not the centroid C, this is the little c. C is 3.25 minus 2. So it's 1.25 inches away from the centroid. So this gives us, what do we got here? 6885. Am I rounding up or down? I'm gonna leave it 6885. So sigma C is 6885. I'll go with like 4 significant figures. PSI, and that is also, it's below the centroid. This is in tension, right? Sigma D is easy. The distance from D to the centroid is 0, right? It's right on the centroid. So we just get equal to 0, right? Sigma D, 0. I'm just going to write here on the neutral axis. Finally, I've got sigma E. I better leave myself room for a diagram. 17,900. Now notice here, I don't have to put a sign here. The distance from E to C is 4 minus 3.25. So it's 0.75 divided by 3.25. This gives me 4,131 psi. So sigma E, 4,131 psi, and that is in compression, right? Because it is above the neutral axis. So it's above the neutral axis. It's in compression. We can do the same thing for sigma F. And that distance is 5 minus 3.25. So that's 1.75 inches over 3.25. We see that sigma F is equal to 9,638 psi, and that is also in compression. So now we can draw, oops, let me just quickly draw the diagram and then we'll end. We can draw the beam here. How am I going to do this? Sketch out an axis. I've got a pencil. Let's see, 1, 2, A, B, C. D is a little higher. And you've got E. And you got F. All right, so this is the beam. Looks like this. from the side. And here we've got A, B, C, D, E, and F. And we're going to have, if I can find a ruler here, we draw this sort of skewed a little bit. All right, over here we've got 17,900 PSI, right? And then at each of these points, we've got a different, let's see, what's B? This is 12,390. Point C was 6885. Point D was 0. Point E was 4131. And point F was 9638. And you can look at this as compression and tension. All right, the numbers, you know, above and below the neutral axis. Maybe I should have written compression up here. So that would be how you would do a problem like this, where you have to calculate the stress at a given point inside and then graph that. All right, so I know I went a few minutes over. That's all I have.